Are we on?
Good to go.
Okay. So, so what I want to do is work through the rest of this chapter because there's more than one way to describe rotations. In fact, we've already seen a couple of ways, right? We have the Euler angles, say the ZXZ Euler angles. Right, and there's the ZYZ Euler angles, and then there's this one that we just talked about today, the axis angle. So this is identity plus sine theta n plus 1 minus cosine theta n squared. Right? So obviously there's more than one way. There's at least two ways to describe rotations. Well, if you have ZYZ, that's at least three ways. So I'll call this gamma prime, theta prime, because these angles are not the same. So if I give you a rotation matrix and say, what are the Euler angles for this rotation matrix? Well, the ZXZ and ZYZ will give you, there'll be two different sets of Euler angles, right? You can't just take the ZXZ Euler angles that you extract from a rotation matrix and put them in here. You'll get a different rotation matrix. So that's why I'm using a prime to distinguish between the alpha, beta, gamma that you get for ZXZ Euler angles and what you would get for ZYZ Euler angles. And what I'll do is describe what the relationship between these are. So, you know, if you're at a cocktail party and somebody says, I calculated these Euler angles were alpha, beta, gamma in ZXZ, and ask what are they in ZYZ, you'll be able to answer on the back of a napkin, okay? Back of the envelope calculation. Okay, so, and the trick there is the way that if you take the rotation around the x-axis and you perform a similarity transformation on it. So here's a trick. So these guys are related to, so obviously these are the same except the angle is different. And these two are related to each other in the sense that if I give you R1 of beta, which is the matrix 1, 0, 0, cosine beta minus sine, negative sine beta, cosine beta. If I give you this matrix, then if I multiply it on the one hand by, I'll move this over here, oops, R1 of beta. If I multiply this on the left by R3 by pi over 2, and on the right by R3 of negative pi over 2. Okay, something interesting happens. Let's see what happens. So R3 is a rotation around the z-axis, and we're talking about a rotation by pi over 2. So cosine of pi over 2 is 0, sine of pi over 2 is 1. So that's what we're talking about for R3 of pi over 2. Now on this side, if we multiply by R3 of negative pi over 2, that's just going to be the transpose because that's the inverse. So if I give you a rotation around, here's a general fact about this thing over here. A rotation around n by negative theta is equal to the inverse of r of n and theta, and the inverse for a rotation matrix is its transpose, right? And you can see that directly from the formula here, because if I substitute in negative theta for theta, then cosine of negative theta is the same as cosine of theta. So this doesn't change. I haven't changed the little n over there, so this hasn't changed, this hasn't changed, this hasn't changed, but sine theta changes. Sine of negative theta is negative sine of theta. And so, and remember that this is skew symmetric. So if I take the transpose of this, the transpose of the identity is the identity. The transpose of n is negative n. And the transpose of n squared is n squared, because this is symmetric. And so you can use this formula very easily to verify that this is true. So I'm using this as a special case just to say that with a rotation around the 3-axis by negative pi over 2 is just the transpose of R3 of pi over 2. So I don't have to recalculate, I can just write the transpose of that first matrix down over here, and I get this. So if I multiply out the first two matrices, and I'll leave the third one here. So I multiply the first two out, I get 0, 0, 0, can't be 0, 0, 1, 0, okay. And then I get a negative cosine beta, 0, sine beta. And then over here, I get a sine beta, 0, cosine beta. Okay, does that look right? Just matrix multiplication. And then I multiply this one. And then what do I get? I get a cosine beta. Then I get 0. And I get a negative sine beta. And then when I multiply this out, I get 0, 1, and then I get 0. When I multiply this out, I get sine beta, 0, cosine beta. Does this look familiar? I have a 1, zeros, cosines, sines. This is a rotation around the 2-axis by an angle beta. Okay? And so this is kind of interesting, at least to me, I mean, which is that this thing right here is equal to R2 of beta, this whole thing. So we can relate the Euler angles in ZXZ and ZYYZ to replace, so I could do the opposite as well, but let's go this direction. So if I have an R2 of beta prime in here, then I can rewrite that using that formula right there as R3 of pi over 2, we'll squeeze that in there, R3 of pi over 2, R1, now this was a beta prime here, so this has to be a beta prime, R3 minus pi over 2. Now, in general, rotations don't commute, but rotations around the same axis do commute. And the angles add. So this is an R3, this is an R3. So we can write this as R3 alpha prime plus pi over 2, R1 beta prime and then this is an R3 and an R3 multiplying each other, which is R3 gamma prime minus pi over 2. So the ZXZ Euler angles and the ZYZ Euler angles, while they are not the same as each other, you can easily interchange. So if I tell you, here's a rotation matrix R, I just give it to you in terms of numerical values, right? I give 0.1, etc. It's all the entries in the matrix are given as numbers, and I say, okay, the ZXZ Euler angles are such and you could go calculate them, and you could go calculate the ZYZ Euler angles, but you would sort of be wasting your time if you did both separately, because as soon as you know one of them, you can very easily calculate the other, because here we have a 3, 1, 3, here we have a 3, 1, 3, which says that the ZXZ Euler angles, alpha, beta, gamma, are related to the ZYZ Euler angles, alpha prime, beta prime, and gamma prime, by these simple formulas. Okay? So if you know the ZXZ Euler angles and you want to find ZYZ Euler angles, you would just bring this over to the other side, right? So I guess the take-home message is the beta is the same for ZXZ and ZYZ Euler angles. But the alpha and the gamma differ by pi over 2. Okay? So, but we can interchange between ZXZ and ZYZ. Okay. There's a couple of other things that are useful. So when looking at satellite attitude dynamics, not only for this microsatellite problem, but for other satellite attitude reorientation problems, there are other kinds of parameterizations that people use in the field. Not only Euler angles and not only this axis angle parameterization. Another that's commonly used is to say, let x be theta times n. Then since we know that r is equal to the exponential of theta n, that's the same as saying exponential of x, where here x is, again, because n was skew symmetric, x is a skew symmetric matrix. And the so-called exponential parameterization or just the exponential parameters give you a rotation matrix that we can call R of x. So this x is not the vector in three-dimensional space that gets rotated. This x is exponential parameters corresponding to little x1, little x2, little x3. And this is going to be related to R of theta n, R of n and theta. The only difference is that what is the relationship between n, theta, and x? Well, theta is the square root of x1 squared plus x2 squared plus x3 squared. And n is equal to x, and so of course this is just the magnitude of the vector x. And little n is the vector x divided by its own magnitude. So in a sense, the n theta description of rotation is kind of like polar coordinates or spherical coordinates that you describe instead of, but we're not talking about a point in three-dimensional space. We're talking about taking a rotation matrix and describing that in polar coordinates. That would be n and theta. and x is more like Cartesian coordinates, and you can convert back and forth between polar coordinates and Cartesian coordinates, and sometimes one is more convenient to use than the other. But it turns out that if you take the formula for r of n and theta that I gave you, and you use these conditions, little n is equal to this, and theta is equal to this, then we can write r of x is equal to the identity plus sine of the magnitude of x divided by the magnitude of x times x. So this came from x divided by the magnitude of x. That's like that's capital N. This one is theta. And then over here we have 1 minus cosine of the magnitude of x divided by the magnitude squared of x times x squared. So this squared is because we're taking capital X divided by this magnitude, which was n, and that n was squared. So this is basically the same formula as before, but it turns out that there's a difference in that, just like in polar versus Cartesian coordinates, in polar coordinates, if you want to ask questions like, when you do integration or calculate gradients and do other things in polar coordinates, you have a singularity at the origin, right? Because you have a Jacobian determinant that looks like, in the planar case, in polar coordinates, you get an r, or in 3 dimensions, you get r squared sine of theta. And if you're in Cartesian coordinates, your Jacobian is always just equal to 1. So there are contexts, and we'll talk, because we're going to be talking about Jacobian iterations and what that means. The Jacobian matrix for this kind of exponential coordinates is better conditioned than the Jacobian matrix for Euler angles or for this axis angle description of rotations. And so, we're going to just finish our discussion of different ways to parameterize rotations, and then we'll talk about what it means to be a Jacobian matrix for a description of rotations, and then that'll lead back into the discussion of inverse Jacobian iterations, and we'll go back to the robot arm example, and then from there we'll put these two things together and finally finish that satellite reorientation paper. But this is all culminating in a big homework, not like the little homework I gave you for Thanksgiving over 2 weeks, including Thanksgiving. But this will be a larger homework assignment involving some computing. Okay, so let's round out the discussion of rotations and all the different ways to describe rotation. So now I'm talking about from page 114, 115 through 117. So we're sort of skipping around in this chapter 5 that I sent out. Okay, so and these are sort of useful factoids for anybody who does computations with rotation matrices. So we're gonna do something that's very similar to what we did when we calculated. So I gave you some theorems before in the context of mx double dot plus kx equals 0, the matrix version, where we used properties of symmetric matrices that the eigenvalues of symmetric matrices are real numbers, that the eigenvectors of symmetric matrices corresponding to distinctly different eigenvalues are orthogonal to each other, right? And there was kind of a slick proof of those facts that we went through. I'm going to do something similar to prove properties of the eigenvalues of rotation matrices. So rotation matrices in general are not symmetric. There are symmetric rotation matrices. So for example, the identity matrix is symmetric. And the matrix -1, -1, 1, which is a rotation around the z-axis by pi, is symmetric. Likewise, the rotation around any axis by pi is a symmetric rotation matrix. But in general, even though there are special cases where rotation matrices are symmetric, in general, they're not symmetric, right? If I have a cosine over a cosine, I have a negative sign here and a sign there, it's usually not, they're not equal to each other. Only when they're equal to 0 is it equal to each other. So rotation matrices in general are not symmetric, although they can be in specific cases. So we're not going to use exactly the same proof as we did when looking at symmetric matrices, but it'll be the same style of proof. So if I give you a rotation matrix R, and I multiply it times a vector, then the condition for this to be an eigenvector is that this holds, where lambda is a scalar. Okay? So I can take that expression and I can conjugate the whole thing. And we discussed this before. If I take the complex conjugate of the product of two things, that's the same as separating out. So the complex conjugate of this whole thing is the same as the complex conjugate of this times the complex conjugate of this. And likewise on the right-hand side. And so what we can then do is take both of these expressions and take their dot product. By the way, we know that the complex conjugate of a rotation matrix is just the rotation matrix itself, because a rotation matrix has all real entries in it, right? You don't have complex numbers in a rotation matrix, and the complex conjugate of any real number is just that real number, okay? So now if we take these two equations and we take the dot product, we'll take the dot product of this with this, then that must be equal to the dot product of this with this, right? Because these are both equal to each other. So we get RV dot product with RV complex conjugate is equal to lambda V dot product with lambda complex conjugate, like this. Now, when we talk about a dot product, that's the same as taking the transpose of this. And so this can be written as V transpose R, V complex conjugate. Now these scalars we can bring all the way out front. So this is lambda times lambda complex conjugate. This is V transpose V complex conjugate. What's R transpose times R? I mean, I know it's late in the afternoon, but it's not that late, right? It's not a tricky question.
Identity.
It's the identity. So, so this simplifies to V transpose. So this right here is the same as this right here. And it's not 0 because we always exclude V equals 0 from consideration when talking about eigenvectors. So we can divide both sides by that. So we get the identity is equal to lambda times its own complex conjugate. Okay? So that says something kind of special about the eigenvalues of a rotation matrix. And so there's only one way that that can hold. And this is also from another result of Euler, which is e to the I theta is cosine theta plus I sine theta. And the derivation of this is pretty much the same as the derivation of r of n of theta, okay? You do a Taylor series, you recollect terms. In this case, you recollect terms into real and complex parts, or real and imaginary parts. In the other case, we had a matrix n, and we had the powers n to the 1 and n to the 2. But in any case, the only complex numbers that satisfy this are complex numbers of the form e to the I theta. Because if I take the complex conjugate of this and I multiply it times itself, e to the I theta times, the complex conjugate of this is e to the negative I theta. When I put them together, it's e to the theta minus theta. So e to the 0 is 1. So it turns out that the only eigenvalues of a rotation matrix have to be of this form. So then the question is, what is theta? How is theta related to the rotation matrix? Well, there's one degenerate case, and that's theta equals 0. Because if we go back, if you believe me that any rotation matrix can be described in the axis angle form, if I take this and if I multiply this by n, okay, if we go back to the derivation of the Rodrigues formula and Euler's theorem, if you multiply, if the vector x that we were talking about back then is replaced with n, well, n, the axis of rotation, doesn't change under the rotation. That's the only vector that doesn't change. N and multiples of n. The axis of the rotation stayed fixed under the rotation. And you can see that from this formula, because if I multiply over here by n, then I'm going to get I times n is n. Capital N times little n is little n cross little n is 0. So this doesn't contribute. And then this is just capital N times little n. But capital N times little n, you can do this part first, and that's 0 again. So what that means is that the vector n pointing along the axis of rotation stays fixed under the rotation. But another way to write that is that that's equal to the number 1 times n. So in other words, every rotation matrix, every 3 by 3 rotation matrix, has as an eigenvector the axis of rotation, and has an eigenvalue, the number 1. Okay? So that's a very special case of this, where theta is equal to 0. And it turns out that the other two eigenvalues are plus and minus theta, e to the plus and minus I theta. And we can get that by going back to what I had before, which was writing this in this form. So the eigenvalues, as a general linear algebra fact, and the eigenvalue of the matrix, let's say, BA, B inverse, are the same as the eigenvalues of A. In other words, eigenvalues do not change under a similarity transformation. And that's exactly what we have here, because Q transpose is equal to Q inverse. For a rotation matrix, the inverse is equal to the transpose. And so the eigenvalues of a general rotation matrix, like this, which is the same as a rotation matrix like this, the eigenvalues will be the same as the eigenvalues for just the matrix R3 of theta. Okay, so if I give you the matrix R3 of theta over here, cosine theta, negative sine theta 0, sine theta, cosine theta 0, 0, 0, 1. Okay. If I ask what are the eigenvalues, well, we can go through and calculate the characteristic equation. So if this is R3 of theta, and by my argument over there, the eigenvalues of any rotation matrix are going to be the same as the eigenvalues of R3 of theta, because the Q doesn't matter when it comes to calculating eigenvalues. It does matter when it comes to calculating eigenvectors, but that's not the question here. The question is, what are the eigenvalues of a rotation matrix? And so we calculate the determinant of R3 of theta minus lambda times the identity, set that equal to 0. That gives us a characteristic equation. So in this case, that characteristic equation, we're going to go minus, minus, minus lambda. And we calculate this determinant. This is easy because we have rows and columns intersecting that have zeros except for here. So this is 1 minus lambda times the determinant of this block, which is cosine theta minus lambda squared. This times this minus this times this, which is plus sine squared theta, is equal to 0. Now if we expand this out, this is going to be lambda squared minus 2 lambda cosine theta plus cosine squared theta. Cosine squared theta and the sine squared theta add to 1. They sum to 1. This gives us lambda equals 1. We knew that already from the argument that I made over here, that the vector n was an eigenvector with eigenvalue equal to 1. So let's just concentrate then on this. So once we add, so I expanded this out, but we add the sine squared theta in, that gives us a 1, because cosine squared plus sine squared is equal to 1. This is just a quadratic equation. So lambda is equal to, what's the quadratic equation? Let's see. Ax squared plus bx plus c equals 0. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, if you show my